Precalc Chapter 7. This is actually not in Chapter 7, but we've added to the chapter because it uses our system knowledge. So it's how to solve linear programming, and we'll use some systems within the technique. And so the A113, the A122, this is the appendix pages you can go to find the sections in the problem set. We're going to be optimizing problems, and we did that a little bit in Chapter 2 with quadratics. When you optimize is by finding the max or mins of quadratic equations. Those of you who had me for try A, we did it when we were looking at like rectangles, like fenced-in areas. We maximize the area. That's kind of an optimization problem. We're going to do it some more today, and it's just finding the minimum and maximum values that work. You also did that for your project, Part B, where you minimize the cost for the given gallons of gas that would fulfill the constraints for the octane levels of the car. So we're going to do for a two-dimensional linear programming. And so two-dimensional, we're only looking at x, y. It's not three-dimensional like you did in your project. So it's a little easier, less constraints. So the objective function is the quantity to be maximized or minimized. So the objective function is the one that you're concerned about. So like the project was the actual money, the cost of the gasoline we wanted to minimize for that example. And so this is called the objective function. The constraints are the sets of feasible solutions. So you have to fulfill the constraints first and then test the values in the constraints to see which ones will maximize or minimize the objective function. So the solutions to the linear program occur at the vertex of the set of feasible solutions. The vertex meaning on the graph. So if you look at the graph and where are the vertices, or where are the linear equations. And so the steps to go through is to first sketch the systems of constraints. It gives you a visual perspective of where the vertices would be. You can find the vertices, find the actual vertice points that are the solutions, and then you're going to test them, test those points in the objective function. And so this is what we did for the project when we actually found the possible values that fulfill the constraints, and you tested them in the money equation to figure out which one minimize the cost. So we've already kind of done this a little bit. So if you have a bounded region, which means the shape that you sketch out has sides all the way around it, then both a max and min will occur at the different vertices. If it's unbounded, meaning it goes forever in one direction, then the solutions, if solutions occur, solutions still occur at the vertex. You may not have both a max and min, but if there is a solution you're looking for, it will still be at a vertex. So when you're given these problems, you're given like the objective function, and you're told like here we're going to find a max, and here's our objective function. So we have z equals 2x plus 4y. So this is what we want to max, is find the biggest possible z value given these different x and y values. Now the constraints means that we have to fulfill all of these constraints still need to work. So only the x and y values that make all of these inequalities true would then work for this equation, or could be possible solutions for this equation. And so we first want to graph this system of inequalities. So if we do that, let's graph the first one in purple. X is greater than or equal to 0. X is greater than or equal to 0. When we graph that, we graph first the equation x equals 0, which is this vertical line. And again, we draw it solid because it's or equal to. X values are bigger than that, which means we would shade the right-hand side of that. Now we shade one side of that. So that's the purple one. Then we can do the y is greater than or equal to 0 in orange. So we have the horizontal line at 0, and then above it. So those first two constraints pretty much just make us have a solution set that's the first quadrant, which happens a lot in real life examples where it doesn't give us any negatives then. So the next one's doing red. 2x plus 2y is less than or equal to 10. A fast way of graphing that is using intercepts. So here the x-intercept, 10 divided by 2 is 5. So 1, 2, 3, 4, 5 would be the x-intercept. The y-intercept is also 5. And then I can connect those 2 points, and that would be the. Now these are all or equal to I have here. If it was not or equal to, then you have to draw the dashed line. Just kind of remember that from previous math. Now to figure out what side I shade here, I could test the point 0, 0. So if I put 0, 0 into the equation, I get 0 is less than or equal to 10, which is true. Because it's true, I want to shade the same side as the point 0, 0. So I would shade this side of that line. And then let's do the last one on blue. X plus 2y is less than or equal to 6. So again, the y-intercept would be 6 divided by 2, 3. So then connect these two. And then we need to figure out what side to shade. Again, plugging 0, 0, 0 in that equation, you get 0 is less than or equal to 6, which again is true. So I'm shading below that again. So now I need to figure out where does all the shading overlap. And the shading will overlap in the area bounded by those segments. So that green shaded area is the solution set to these constraints all right there. Now, our possible solutions to the objective function is going to be found at the vertices. So we're talking about this point here, and then this point here, which is the solution of the blue and red graph, where those two intersect. And so I'm guessing it's 4, 2, to make sure we can plug them in to make sure it works for both of these equations. If you want to solve this algebraically, we can do that as well. That's pretty easy to do. We can actually just subtract them. If I subtracted those two, 2x minus x is x. We get no y's. 10 minus 6 is 4. If I divide, actually x is 4, so that's our value 4. If I back substitute that for x, I find y is actually 1. So it should be 2, 1 is where they cross. So let's write down the possible solutions. We have the solution 0, 0. So we have like an xy table we can make here. We can do 0, 3. We can do the 4, 1. Or we can do the 5, 0. These are the 4 vertices of this bounded region. We then need to test all of these in the z equation. So I can make a third column here, z, and let's plug in. If x and y are 0, then z is 0. If x is 0, y is 3, and this equation up here, so 0 for x, 3 for y, then z is 12. If x is 4, y is 1, we get 8 plus 4, 12. And then if x is 5, we only get 10. So then we have these 2 points are the solutions. So it's between the 0, 3 and the 4, 1. Now we can check other points along this. So let's plug in 2, 1, 2 into the blue equation. If I plug 2 in for x, we get 2y equals 4, then y is 2, so that'd be the point 2, 2 right here. Let's plug that in our equation up here, and I get 4 plus 8, which is also 12. So notice how because the two vertices, these two vertices, let me show you another way, highlight that. Between these two vertices right here, both vertices have the same value. Whenever that occurs, then all the points between those two vertices would also have the same maximum value. And so the solution that would actually maximize this function, we could say, so the maxims are at the x values between zero and 4. We're going to include those values, so that's the interval notation, on line, and we can state the line they're on, the x plus 2y is equal to 6. So these would be all the possible points that would actually maximize that z function. I'll quickly try to get through one more problem here. So a gold processor has 2 sources of gold ore, source A and source B. And in order to keep his plant running, he needs at least 3 tons of ore. So A is the amount from source one source, B is the amount of tons from the other source. So the amount A plus the amount B that they're going to be processing has to be at least, so greater than or equal to the 3 tons they need. Ore from source A costs $20 per ton, and then the ore from source B costs $10 per ton. The cost must be kept less than $80 per day. So 20A is what it costs for the A source, and then 10B needs to be less than or equal to the $80 per day to produce or to process. The federal regulations gives you some constraints that source B cannot exceed twice the amount from source A. So if I double A and I have B, the amount of B has to be smaller than or equal to the 2A. And then the last one here, we have the 2 ounces of gold per ton for source A, and source B gives us 3 ounces of gold. So we have 2 ounces for source A and 3 ounces for source B is what we can get back for every ton we process. And that's our goal, is to get the most amount of gold, so we want to maximize that. So here's our constraints. And so you have to pull that from all of these sentences, which is pretty difficult. There's a lot of math that's occurring there. So now let's actually sketch this, and I already have the graph kind of done for time. So A plus B is greater than or equal to 3. That's just going to be this equation here, and we're going to shade above that. If you test the point, what side you'll shade. We look at 20A plus 10B is less than, so now you're shading below this one here. So you kind of see we're looking at this region between these two lines. Then our third one here, 20A is greater than or equal to B, you'd actually shade below this line. And I can find that out by testing a point, testing this point here, knowing that this is axis for A, this is the axis for B. And so if I point the 3, 0 in there and plug 3 in for A and 0 for B, I get a true statement. And so I need to shade this side to make it true. So it is true. And then the region bounded by the overlapping would be this region right here. Put it in blue so it's darker. So this would be the region we're looking at. This is the solution, all the possible solutions for those constraints. And so now the actual vertices when you look at are these 4 points. So we can take and make a table for that. So we have A, B, and then our maximum amount of gold. So we have our 3, 0, and then we have 4, 0, 1, 2, and then 2, 4. Those are the 4 points, and you can double check those are the intersection points at 1, 2, and 4, 2, or 2, 4. And those will be the values. Now put these into the equation, and you'll find a value of 6, 8, 8, 8, and then 4, 12, and then 18. So obviously this one right here is going to maximize the production of gold. So you want 2 tons from A, and you want 4 tons from B. And that will produce the maximum amount of gold you can get. We'll call that good.